Hey everyone, Morgan here. So we are on page 4 of the lecture outline dealing with bonding and Lewis structures. And we're going to be talking about a theory called VSEPR, which stands for valence shell electron pair repulsion. And what this really means is we're talking about the shapes of molecules and what they're going to look like. Okay? Now, the two simplest types of molecules that I can address are ones that are diatomic, like this one right here. Okay? Two atoms. The only thing you can do geometrically is put them in a straight line. Or this, okay, and what we have here is a central atom, which we'll call A, and then two substituent atoms that we will call B's, and in either case, these are linear molecules. Now, it's probably important to note that the bond angle for both of these is 180 degrees. Okay? What you're trying to do is get the atoms as far apart from each other as you possibly can. Now here we have a triangular, or what some people would call, let me write this in, triangular planar. Now, we have our central atom A, okay? We have three substituents, which we are calling B. This is basically a circle divided into three equal parts. So these are 120 degrees. Now this is also something that's flat. I cannot push my pen underneath it. It is lying in a plane, and maybe it's more obvious when I stand it up like that. This is lying in a plane. Okay? Now what's happening is the electron clouds that I'm trying to represent there with my hand, okay, those are pushing the atoms to be as far apart as possible. Okay? Now, it is possible that one of those would pop off and this would bend down a little bit, and we would call that an AB2E, with the E representing the lone pair. Okay? Now, the lone pair will cause a little more repulsion than the atoms themselves. This will be a little bit smaller than 120 degrees. Okay? We would typically just say less than 120. And in this table, please note I've always got examples here. Okay? Now, for the tetrahedron, and I love talking about these. This is basically a pyramid, right? This is an old four-sided die that I had from my Dungeons and Dragons days. Okay? 4 sides to it. Okay? That's what this is. A face here, 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 and then the face that's on the bottom. Okay? Tetra for 4, hedral for faces. Now, the angles are not 90-degree angles, because when it pushed out to being three-dimensional, you can see, hey, look, my pen can go underneath that. We got up to angles of about 109.5 degrees. All right? Now, it doesn't matter which way I hold this, it basically looks the same. Now, if one of the atoms comes off and I get a lone pair replacing it, the electron repulsions off of this lone pair will push these down a little bit more, and depending upon what the atoms are, 107.5 degrees. And if it's 2, we get something here that kind of looks like Mickey Mouse ears off the top, okay? And this is 104.5 degrees. It's just a little bit of a change each time. These are all the same basic shape that have been distorted. So each time we have 4 electron domains around the atom, except that in this case, they're all shared with another atom. In this case, 3 are shared with another atom. 1 is a lone pair, or here, 2 are shared with another atom, and 2 lone pairs. Now, I put up a link for a model kit from Amazon that if you are so inclined, you're welcome to buy. I'm not requiring that, but it really does help in understanding these shapes. If not, I recommend that you get some marshmallows and some toothpicks and you do the same thing at home. You really do need to know all of these shapes. That is important. Now, triangular bipyramidal for when 5 things are attached, what we call the AB5 molecule. One that's up and one that's down. We have a straight line here. 3 that are around the middle. So it's almost like I took a linear and a trigonal planar and put them together. Okay? So 180 degrees here, 120 degrees between the lighter green ones, and then between the dark green and the light green, 90 degrees. Those are my different bond angles. Okay? Triangular bipyramidal. Now, if I take one of these atoms off and replace it with a lone pair, I get this, which is typically called a seesaw, although the technical name is irregular tetrahedral. If I take 2 of them off, and they always come off from around the center. These ones that are straight across from each other are called axial, and the ones around the center are called equatorial. So in this case, I get something that we say is T-shaped. And then, if I go one more lone pair, I'm back to linear. 3 lone pairs equatorially, and then atoms out here which are axial. Okay? Now, the next one, octahedral, is kind of like an 8-sided dice, if you remember these polyhedral dice. Okay? So, this is what these are. I've got 4 around the center, which you can see there. 1 up, 1 down. So, pretty much I've got 90-degree angles and I've got 180-degree angles. If one of these were to come off, it becomes what we call square pyramidal. Notice I took off one of the dark green ones. Then if another one comes off, okay, I get what we call square planar. It's flat. Everything lies in a plane. And it is actually possible to have one where there are 5 things around the middle, 5 things equatorially. I don't have anything that can do that in a model. Not that many examples of it. The only one I know of is IF7, which we call pentagonal bipyramidal because there'll be 5 around the center. Okay, it's time to get to work on memorizing all of these. These are important, okay? We're going to use these shapes a lot. Okay, that's all for this video. We'll come back in the next one to deal with resonance.